Hi, thanks for joining us for Phosphorus Science Now. I'm Matt Scholz with the Sustainable Phosphorus Alliance, and I'm joined today by Dr. Brooke. She's going to be discussing a paper that was recently released in Environmental Science and Technology, on which she's the co-author, and that paper is called Managing Diffuse Phosphorus at the Source versus at the Sink. Brooke's research focuses on physical chemical treatment processes for water and wastewater treatment, and related to phosphorus, her work mainly targets improved opportunities for phosphorus removal and recovery from waste streams. So Brooke, thanks so much for joining us for Phosphorus Science Now.
Thanks so much, Matt. It's good to be on with you.
Yeah, and it's an interesting paper. You've been working with folks on this for quite some time. I know because I remember we were talking about this paper, I don't know, maybe a year ago even.
Yeah.
Do you want to tell us about your co-authors?
Yeah, this has honestly, like you said, been a pretty long process. It's kind of the culmination of a couple years worth of work that we did as part of the National Science Foundation's Phosphorus Research Coordination Network.
Right.
So it combines a lot of different people from a lot of different backgrounds and perspectives, and also an international-based team. So we have experts in agriculture, and we have experts thinking about phosphorus in the environment in terms of lakes and biogeochemical cycling. And also people who have a little bit more focus on a removal and recovery side of things. And so, again, from across the world, from Ireland and New Zealand, US, and all over the place. So it was a pretty good mix of people to get some good perspectives on how we're actually managing diffuse phosphorus.
Right, and you have a Stockholm Water Prize co-recipient. That kind of raises the profile of the paper.
Definitely. So included on the paper was Dr. Bruce Rittman, who just recently won the Stockholm Water Prize. So we're very proud of him there and happy to be able to work with him as well as the rest of the team on this.
Okay, great. So can you tell us a little bit about the context in which you wrote the paper, why you wrote it, what your objectives were for writing it?
Yeah, absolutely. So I should mention, along with the whole team there, this was really led by Dr. Katrina McIntosh. And so I'm going to be speaking on behalf of everybody today. But like I said, we come from a variety of different backgrounds, and our overall goal was to think about how we could better manage diffuse phosphorus. So if we think about diffuse phosphorus in general, we know that we're losing phosphorus along the food chain from growing plants all the way up to consumption, and that we have different sources that are coming in from both point sources and diffuse sources. And we've done a pretty good job at general in thinking about point sources. So we're all pretty happy with that. We can see reductions, but the bigger kind of question that's hanging out there is this diffuse phosphorus question. So how are we going to better manage that? So this got our conversation started. And all of us come from these different backgrounds where we had different ideas of what are some diffuse management options. So we kind of brought those together. And of course, thinking about, we know that they're spread out and that they're periodic in nature, so they're tough to deal with. And that's why they've kind of been last on the list. But as we start to improve phosphorus management in general, we know that we're going to have to start addressing diffuse phosphorus better. So that was really the impetus behind our paper.
Right. When you talk about diffuse phosphorus, just can you define that more specifically for us? It's what doesn't come out of a pipe. Is that pretty much?
Yeah, you nailed it. So we basically defined it as point sources are things coming out of a pipe. So we have a kind of a centralized system versus diffuse phosphorus not at a centralized location. So it could be coming in from agriculture, or thinking about it in terms of cities, or even in the natural environments themselves. And you can see in this picture, these were some of the different types of diffuse sources that we addressed in this study.
Then what were your objectives? What did you set out to do?
So in terms of objectives, we set out to answer a couple of big questions. And so the first was thinking about how quantity and form of diffuse phosphorus vary across our different settings. So whether it's an agriculturally dominated landscape or crops, or in cities, or in the aquatic systems or lakes or the sinks themselves. We thought about this in terms of what are some best current practices that are in play right now. So again, ranging across that whole system of what can we do on farms, but what can we do in cities, and are there options to actually deal with this diffuse phosphorus in the sink and do it effectively. So this brought up the question, we do a lot of management at sources, and that makes good sense, but sometimes there are needs and alternatives where we can actually deal with it in the sink. So at the end of all this, thinking about the management options, we also considered, when is it best to think about reductions in source, or to think about removal, or to turn to recovery of phosphorus and then put it back into play in a more of a circular economy type of setting.
Great. And so let's go ahead and jump into some of the figures in your paper. I think you started out here with one on just quantifying the flows of phosphorus from these various sources.
Yeah, so our first question when we looked at this process was to say, hey, how much P is there and where is it occurring at? And so we tried to do this from more of a standard metric because we know across all these diverse systems, people track and report phosphorus loadings in different ways. And so we kind of standardized it to an annual surface loading in terms of the mass of phosphorus per surface area, hectares in this case, per year. You can see here in this table the ranges that we found for different agricultural-based systems, as well as some cities, considering if we had low or high density populations, and also some numbers that were given for aquatic sediments in terms of freshwater sedimentation.
And these have pretty big ranges, these numbers.
They do. We found some big ranges, and they reflect really a global basis. So we know that there's going to be huge differences in how intense, for example, an agricultural operation is, or how dense a city is. And so you can really truly see this reflected. And it was interesting because you can see, for example, if we look at a high density city, we actually have a pretty high phosphorus annual surface loading. But when we think about this in terms of agriculture is probably taking up more surface space. So in the end, we're going to have higher quantities of phosphorus in those locations. But these ranges kind of helped us to track them down and think about where that phosphorus is occurring.
Sure. And do you have any sense of the scale of some of the other sources, for example, forests loading into water, or aerosolized phosphorus or anything like that? Would these even register on the scale, or are they much smaller?
It's a good question. I don't have the specific numbers compared to these values, but one of the systems that we looked at in our case studies that maybe I can talk about here in a little bit was our Everglades system. And from that case study, we were able to track down some of those numbers and see where inputs from, for example, atmospheric deposition and rainfall, as well as birds and animals in the environment, how they kind of start to compare to some of the human inputs.
Okay, great. So go ahead and walk us through the next slide.
All right, so after we thought about how much phosphorus there is, we also considered what form it's present in. So it makes a difference if it's soluble or particulate or reactive or non-reactive. And all those things matter because it dictates its behavior in the environment. So if it would cause a problem if it's present in excess, and they also start to impact how well we can remove and recover phosphorus.
Okay, great. And so after that, I think you go into some examples of how to actually manage this stuff once it's in the environment.
Yeah, so we use these two big metrics of P, quantity, and form, and we started to apply them to some different current practice examples. And so we took a number of examples from across the world from different areas, whether that was agriculture or urban or aquatic systems. And we started to track down that quantity and form and think about what sort of management options were in practice and use these to draw on where we could apply them to different jurisdictions at a global scale. So you can see here a couple of the examples that we really focused in on and did some detailed lit review. So in terms of agriculture, we thought about phosphorus use efficiency in livestock dominated agriculture. So that was our Ireland case study. We also looked at it in terms of crop-dominated agriculture. So that was a case study at Albert Lee Lake Watershed in Minnesota. And we looked at New Zealand in terms of some mitigations that occur on the farm. So in general, that case study showed us that cost is generally going to increase as we increase in distance from the source. That makes sense. But also pointed out that we can do some kind of creative ways of approaching that mitigation. So if we can target areas where we know that there's going to be a lot of phosphorus loss, but perhaps it's a smaller land area, it's also going to help us keep those costs down. So it really highlighted some of the critical sources.
So what about the urban and aquatic systems then?
Yeah, so like we talked about before, the urban is interesting because it has less of a quantity in comparison to agriculture. But it's an interesting system because there can be a lot of different inputs, and unlike agriculture, these might not necessarily be taken out explicitly. So even in terms of small inputs, they can make a big difference in an urban area. So we looked at a couple studies there. One was Minneapolis, St. Paul region in Minnesota, which has some really good documentation on the impact of things like landscape fertilizers. And in that setting, they've actually ended up banning phosphorus landscape fertilizers. And so beyond that, they could look at inputs of phosphorus, including pet excrement and removing and recycling vegetation, and as well as kind of the general urban stormwater best management practices. So we also looked at urban systems in terms of septic systems, and we found that they generally accounted for at least an order of magnitude lower in comparison to agriculture and kind of our urban wastewater point sources. So still a consideration, but probably less magnitude there. So the last system that we looked at was the aquatic system, or the sink. So we know as all these things go downstream, they're eventually going to pile up in the aquatic systems. And so we looked at a few case studies where they're actually implementing some different strategies for diffuse phosphorus management. And the first one we looked at was the Dixie Drain system in Idaho. And this is actually being planned and implemented at this point. And it's an interesting case of point and diffuse pollution trading, because in this case, they found that it was actually more cost-effective to employ phosphorus removal in an agricultural return drain, so more at the sink level, versus looking at upgrading the water resource reclamation facility, or the point source. And so based on a cost-benefit analysis, they found that they could actually remove 1.5 times more phosphorus at the sink compared to at the source for the same cost.
Right.
So a couple other examples, aquatic systems that we looked at Everglades, and I mentioned that previously. It's a pretty interesting case study because it's ultra low concentrations of phosphorus, so it's very limited. Historically, something like 90% of phosphorus inputs came from rainfall. But then as they had greater development in that Florida area, there were greater inputs from agriculture and urban areas. And so you can see on this graphic that we're looking at, they actually implemented some best management practices that were in place on farms and in urban stormwater areas. And you can see drops in the levels of phosphorus. And then they said, hey, we still haven't met our goals, which are ultra low in this case of like 10 micrograms per liter. So further implemented in sink actions where they had wetland systems that were still removing extra phosphorus. And so this is a good example of, like you said, the natural inputs in relation to some of the human inputs. And some of the studies that we read on this indicated that those natural inputs, for example, from birds, were still a really small percentage compared to any of the inputs that we can look at from agriculture and urban areas in the setting. And the last example I want to point out here really quickly is that we also considered the importance of internal phosphorus loading. So here you can see a range of different lakes that were selected from the Midwest and Europe, and you can see the different inputs and different relation of external loading to internal, which it has huge variation, but it points out that in some cases that internal loading from the sediments can play a really big role, and so has to eventually be considered. So it could be things like dredging of lake systems, or mitigating that in terms of adding lanthanum, for example, and trapping that phosphorus in the sediment.
Yeah, great. And there's just recent research that's come out that's shown that that sediment phosphorus tends to stick around for a long time.
Yes, definitely can't forget about that.
Yeah. Okay, so next in the paper, you developed something called the P4 matrix. Can you walk us through that?
Yeah, thanks. So we actually took all those different case studies that we looked at, and we started mapping them onto this matrix. And you can see that the matrix in the vertical dimension, we were assessing from organic to inorganic forms. And on the horizontal dimension, thinking about, is that phosphorus present as particulate or soluble? And we know that in any of these different sources or sinks, there's going to be a mixture, but we put them in on this matrix according to prominent distribution. And so we wanted to use this as a good tool to better assess what our opportunities are for different PMAT management strategies. So one of the things that we can see is in this lower right-hand corner that it's pretty much largely unoccupied. But on that basis, we can start to track down the other three quadrants. So in our third quadrant, we can see This is the bottom left-hand corner. This has the greatest opportunity for total value. And we think about that in terms of there's phosphorus that's a resource for recovery, but also you have a lot of organic rich substances in this matrix. And anytime we have that, we might have a lot of opportunity to co-recover things like nitrogen and energy. Versus if we look at more of the soluble inorganic form in that upper right-hand quadrant, this probably offers the best opportunity for recovery of pure products. So we can think about this as phosphorus with less of the other substances that we might not want to co-recover to put into play as a fertilizer, for example.
Okay, great. And then you lead in the paper, you go into a section about how to frame all this, essentially the hierarchy of interventions.
Yeah, so we have this spectrum of management options. And one of our take-home messages is that in different settings, any of these possibilities should be open for discussion. So they're going to be more or less relevant in localized settings, but there are opportunities, even as we look at this going from kind of low cost to higher hypothesized cost at the bottom of that pyramid, there's still opportunities to implement some of these different strategies. So, we can start off with our strategy of reducing and conserving on site, which could be things like better phosphorus use efficiency and drawing down soil phosphorus surpluses. We can work our way down to our next layers, thinking about mitigation and remediation on site. So for example, on the farm, and then actually applying things in the aquatic sink. So sequestering and removing might be options if we have to have more immediate changes in water quality that we're not getting from source type of mitigation strategies. And then in our bottom here, we can see that we still have opportunities for phosphorus recovery. They're probably going to be more difficult with our diffuse phosphorus sources, but as we think about, for example, the Everglades, the George Farley Water Prize is specifically looking at opportunities where we can remove phosphorus that's in very diffuse and low concentrations, but also it's an added benefit if we could even recover that and put that back into the more closed loop of phosphorus recycling.
Sure. I noticed you have on the left axis, it's hypothesized cost of implementation. Have you actually looked at numbers of projects that are ongoing to see if the spectrum management options you've listed here is indeed along this axis?
Yeah, so we were careful to make sure that we said hypothesized here. There's a fair amount of literature and case studies that we can look at that in general point out that our cost is going to be less if we're at the source or if we're eliminating those sources, reducing and conserving. So for example, in some of our New Zealand case studies, we saw that on average, there is 7 times more effective mitigation in terms of cost if strategies were implemented in critical source areas. So in general, this would be our trend that we'd follow. But there are cases where it's not always going to be this. And one example would be that Dixie drain strategy, where it was actually improved cost effectiveness when they were removing at the sink itself.
Yeah, it's an interesting project, and I certainly encourage people to read your paper to hear more about that. Can you then take us home? What was your take-home messages for the paper?
Yeah, great. So to kind of wrap this up and put it all together, as we look forward about opportunities for diffuse P management, one of our main take-homes is that there are strategies that are available, and there's more that are coming out and being available all the time. We think it's really important to take into account some standardized metrics. So we need to look at where is the phosphorus so that we can get the biggest bang for our buck, but also what form is it in, and really have some better developed cost assessments over a range of different strategies. So related to that, we also need to think about improved mass balances and flow analyses for a lot of different systems. So we have some great mass balances and flow balances for phosphorus, but they tend to be in certain areas. And so being able to compare across systems would be a really huge advantage looking forward. We think that all of this coming together is really critical as we can start to inform better, improved phosphorus policy, decision-making, and strategies, and really found these on realistic targets and objectives. So what can we do, and what's the best way to go about it? We also think that there's needs for improved phosphorus removal and recovery strategies, but together with the technology, we're also interested in better data and monitoring because those inputs are going to be necessary if we're going to get more refined cost effectiveness of each of our different management strategies. And in general, to wrap it up, we know that management at the source probably makes the strongest economic and environmental sense. As we've kind of highlighted through this discussion, there still are opportunities for sink-based management, and sometimes they're going to be needed if, for example, source management alone is not sufficient to meet the water quality goals or in a sufficiently rapid timescale to achieve the improvement that's targeted in a specific water body.
That's great. So I wonder, are you going to work now more on or turn towards developing some of those standardized metrics? Because that's really a thorny, interesting problem. It seems to be sort of, the mantra of sustainability is if you can't manage it until you can measure it. It really seems like an important piece of this.
Yeah, I completely agree. Those metrics are strongly desirable, but very difficult to achieve. And so I think that's one of the things that as a team of phosphorus researchers that we'd really try to strive towards, that greater standardization of metrics.
Great. Well, I look forward to future papers on that, hopefully. And thanks so much, Brooke, for joining us. It's been an interesting discussion, and this is a great paper. I hope people take a look at it and think a little bit about how we can manage these diffuse sources of phosphorus more effectively. Thanks so much, Brooke, for joining us today.